Okay, let's think about our full steady state solution. Let's write the whole thing in all of its glory. The actual real motion is the real part of this complex solution that we predicted. The real part, just remember, ZS is not real motion. It's imaginary, crazy, complex motion. We need the real part to get the actual motion, x, steady state. Well, that doesn't affect the amplitude. So we have an amplitude times e to the j omega t minus delta s. So the e to the j part will just become cosine when you take the real part. The amplitude is the amplitude. So that's a real number. So that's got f naught over m here. And in the bottom, this crazy square root, omega naught squared minus omega squared squared plus beta omega squared, like that. And then to get the real part, it's the cosine of omega t, that's just the drive frequency, minus the delta steady state is inverse tangent of, I believe it was beta omega over omega naught squared minus omega squared. Multiple close parentheses. Okay, so there's the whole thing, all its glory. Let's now think about how this is going to behave. That's obviously a very complex expression. Let's start taking it apart. First of all, it's just going to oscillate at the drive frequency. That's the steady state part. But let's look at this amplitude term. Remember, this is the steady state amplitude. So you can kind of see that the amplitude is going to depend on a few things. It's going to depend on how hard it drives it. That's not too surprising. If you push harder, it's going to get a bigger amplitude. If it's light, it's going to get a bigger amplitude. That's not too surprising. If it's heavy, it's going to have a small amplitude. But then, really, this is the interesting part. How does it vary as you change the drive frequency? Because we have the drive frequency showing up here in the denominator. Okay? So you can see, if you've seen these kind of functions before, you know this is going to get exciting when the drive frequency is about equal to the natural frequency. Because when that's true, this and this are going to make 0 in the denominator. And there's still this term, but if it's lightly damped, this term is small. Okay? So if this term is small and this term is 0, we have something really small, almost 0 in the denominator, which makes the thing big. Right? So this thing, AS, the steady state amplitude, gets really large around omega naught. And then when you're far from omega naught, this term becomes bigger. It becomes really big because it's squared. And then it drives the amplitude back down. So if we were to plot it, it looks something like this. If you plot omega on this axis, steady state amplitude on this axis, you actually get kind of a finite amplitude down here at low frequency, and then you get a peak near omega naught, and then it tends to 0 at higher frequencies. There you go. And the peak, it's not quite exactly at omega naught. It's a little bit below omega naught. So there's omega naught, and the actual peak is about right there. So if you were to plot this, you get something like this, right? I'm not saying you can just intuitively know that instantly, but you do get this peak. Okay? So this is called a resonance. Whenever you drive a harmonic oscillator like this and it's lightly damped, you get this special frequency where you get a really big response. Okay? So now I'm going to show you that that's the case with this little setup. So this is our oscillator. It's a mass, which is a mirror, on a little steel shim, which just means a thin, springy piece of steel. So that's the mass on the spring. And the laser is bouncing off the mirror, so you can see its position really exaggerated. So if I move this around, you can see the laser beam deflects. Right? So I can tweak it, and you get a big oscillation, which decays. Right? So it's a damped oscillator. The amplitude goes down exponentially in time. I'll do that again. You can't see the instantaneous motion, but you can definitely see the damping of the motion. Also on this stand is this thing, which will shake, and it supplies a driving force. It's not directly pushing on the mass or on the spring, but the whole thing is mechanically coupled. So if you shake this over here, it definitely pushes the back of the spring. All right. So what I'm going to do is turn it on. Let's see, turn it up. So right now it's pushing at 28.4 hertz. And you can see we get a little bit of motion, 28.4 hertz. And what we're going to do is sweep the frequency and see if we can find this resonance. Okay, so 28.4 hertz, okay, we get a little something, a couple centimeters there. And now let me turn it up to 29.4 hertz. And what did it do? When I went from 28 to 29, it kind of shook, right? Shakes around a little bit. Well, remember, we're doing the steady state solution. So we said it might take it time to get to steady state, but it eventually gets to a steady amplitude. That initial part is the transient. Anytime you change something, you kick off a transient. So let's see, let's go up to 30.4. Okay, shook a little bit, but the steady state's about the same. So we're right here. We're in this part, maybe. Let's go 31.4. Okay, it's a little bigger once I got to steady state. And now here is 32.4. Okay, now it's definitely growing. So now we're sort of coming along up here. And 33.4, oh, there we go. Nice and big. 33, oh, it's still going. Maybe it'll never stop. 33.4, that's big. And then if we go to 34.4, then it comes back down. So 33.4 was somewhere up here, right around the top. And now we're down 34.4 hertz, 35.4 hertz, interesting transient there, 36.4 hertz, 37.4 hertz, 38.4 hertz, 39.4 hertz. And now you can see, I'm showing you that it actually really is going towards zero. Remember, on the low end, it kept this constant amplitude. On the high end, it's really going down to nothing. So it really does map out pretty much exactly the, the frequency we said it would. I was trying to get you back on the resonance just to see it again. Let's see how big, yeah, that's really about it. There we go, that's as big as it gets. And if I mess with it, it's got to go through a transient and grow. But what we really calculated was this steady state part. So it seems our answer was correct.